So in conserving momentum, when do we conserve momentum? When there's no external forces. That means the initial momentum must be equal to the final momentum. Or if there's more particles than one, the sum of the initial momentum must be equal to the vector sum of the final momentum. And so we know that if a box is moving and hits another box that's stationary, in the end they're going to move off in this direction. We know if this box was moving in this direction, they'd move off in this direction. And intuitively, do we also know that if we had two boxes and one was moving in this direction and the other was moving in this direction, what direction would they go off in? So let's say we have an inelastic collision and these guys stick together. We know that we can add the sum of the momenta. And these two together would go off in this direction, so somewhere between these two guys would be the direction of their final velocity. How do we do that? We have some m1 and v1 and m2 and v2. And we can't add velocity because you don't conserve velocity. We add momenta. So if these masses are roughly the same and the velocity is roughly the same, we would have P1 that looks like this mass times this velocity, plus P2 in this direction, and this would be my total momentum naught. Now this total momentum must equal the final momentum, so in the end these two guys go off in this direction. Now what if it were a little different, where mass 1 was really, really, really big, like maybe 10 times mass 2? How would that change a scenario? What would be the direction that they would go off in? And so you realize that if this has a much larger mass, this momentum would be much greater than momentum 2. So if momentum 2 looked like this might be momentum 1. And now the vector sum of the momenta are off in this direction, maybe somewhere between D and C. So there's two ways to do that. One, just by adding vectors nose to tail. You could also go component by component. So in a collision like this, you could say the sum of the momentum x final must be equal to the sum of the momentum x initial, and the sum of the momentum y final must be equal to the sum of the momentum y initial. So if you had two different bodies moving in two different directions, maybe this one has a smaller velocity and a larger mass, I could calculate their momenta. Maybe this momentum, mass 1 times velocity 1, would look like this, and this guy would look like this. And I'd say, no, I don't want to use angles. I'm going to separate this into its x component and y component, and this one into its x component, which in this case, keep in mind, is negative. And then I can say I know the total momentum when these things stick together is going to be, in the x direction, it'll be this momentum minus that amount, so you have a little less momentum in the x direction. And in the y direction, it would be this momentum plus this amount. So you could work just finding your x component of momentum, and that would give you your x component of velocity, and the y component of momentum, which would give you your y component of velocity. Lastly, what if you had a collision that was not perfectly inelastic? Maybe it was elastic, maybe it was partially elastic, but you had some velocity here, some m1, and you hit a stationary object, and all you know is you went off, maybe slower, in this direction. What direction would that guy go off in? You might have put down E or F because this is the direction of the sum of these two. But we don't add initial momentum to final momentum. What we know is the initial momentum must be equal to the sum of the final momentum. So there's two ways to look at this. One, we could look at it component by component. In the x component, this guy lost all its x momentum. So this guy must have gained that momentum. And I don't know how fast it is because I don't know what these masses are. But this guy has momentum in that direction. Now this guy got an impulse upward. Where did that come from? This guy must have gotten an impulse downward. And so I know that this guy must go off in that direction. If I wanted to do this holistically with vectors, I would simply say P final, the sum of P final, must equal the sum of P naught. So what's P naught? Initially, this guy's at rest, so here is all your momentum. So here's all your momentum. And so whatever this momentum is, plus this momentum, I know it has to add to this. Let me write this P naught down here. And I have to add these two momenta. Now I can add the velocity times the mass, and I get this, let's say, plus whatever this guy is, must add to that final momentum. This would be P final 1, this guy, and this would be P final 2, this guy. And the sum of these final momenta must equal the total momentum you started with. Is it elastic or partially elastic? That would depend. You would have to do the energy calculation.